In this lesson, we'll look at the change of base for a log function and solve exponential and logarithmic equations. Let's move on to logarithmic equations, and very often we can use the log laws to help us to simplify our log expressions and to solve log equations. For example, we're asked to find x here when we know that log base 3 of 9 equals x minus 2. So we'll start off with the equation, and we'll observe, of course, that the 9 is 3 squared, so we can simplify that left-hand side, which comes out to be 2. So 2 is equal to x minus 2, so therefore x is equal to 4. In this example, we have log base 6 of x equals negative 2. So to solve this, we'll rewrite it as an index equation. So the base is 6, the index is minus 2, and the number is x. So that gives us x is equal to 1 over 36. In our last example, we're asked to solve this log equation. Now we can show off our knowledge of log laws here by absorbing the 2 into the log and making that 25 squared. But of course there's a much simpler way of doing that, simply by dividing both sides of that equation by 2. So don't always jump into the log laws, look for the easiest way to solve the problem. We can rewrite that equation now as an index equation. So the base is x, the power is 2, and the number is 25. X squared is 25. So we need a number that multiplied by itself will give us 25, so we can have plus 5 or minus 5. But the domain of our function there was x is greater than 0, so the only solution is x equals 5. Combining logs into one log can help us solve log equations. So in this example, we have 2 times log of 2 plus the log of x equals the log of 3. Now notice that all of these logs are base e, all the same base, and so we can combine the 2 logs on the left-hand side. The first thing we need to do is absorb that 2 into the log. So we're using the law that says if we have an index in our log, we can multiply it out. We're using that in reverse. So the natural log of 2 squared is, of course, the log of 4. Adding that log means that we're multiplying those numbers 4 times x. So we end up with the natural log of 4x is equal to the natural log of 3. And that means that the 4x has to equal 3. And so the x is 3/4. So in this example, we'll notice that we have log on both sides of the equation, and we have a term without the log. So we'll try to combine the 2 terms with logs and then put the 1 on the other side of the equation. Now firstly, we need to absorb that 2 that's outside the log once again, so that will give us a log of x squared there, and then we'll put the log over the other side and the 1 over the other side to get this equation here. Now because we're subtracting those logs, it means that we are dividing those 2 numbers. Now we don't have a base written here, so it's understood to be base 10, and we can rewrite this log equation as an index equation. That is, the base is 10 to the power of 1 equals the number inside the log. And so we get that equation. Multiplying through by that denominator, we'll have x squared equals 10 minus 20x. Putting that all over to one side, we now have a quadratic equation that we can solve for x. Now we can solve that by trying to factorize, but we don't find factors easily there, so we'll use the quadratic formula. So putting the numbers in for a, which is 1, the b is 20, and the c is minus 10, we'll get our answer there for x. Simplifying that through, we'll get our two answers of minus 20.49 or 0.4881. In the last video, we solved exponential equations by expressing all terms to the same base. With equations such as this one, that's not possible. So the technique we'll use here is to take the log of both sides of the equation, and by using base 10 or base e, we can evaluate our answer using a calculator. So we'll take log base 10 of both sides. Notice that we haven't written the 10 there, it's understood to be base 10. We'll now use the log law that says when we're multiplying two numbers there, we add the logs. Next, we'll bring the power out and multiply that by the log on both sides of that equation. We can then expand the brackets and collect our like terms. So we'll put the x log of 4 over on the other side, and it becomes minus log of 4 times x there. And then we can divide both sides of the equation by the bracketed term there, and we will then find x. We can evaluate that on a calculator, and we'll get our decimal approximation. Notice that we could have used log base e there instead of log base 10 throughout, and we would still get the same answer. Let's see how we can change the base of a logarithm. Now, most calculators only have base 10 or e, so we need to change the base to be able to evaluate them. For example, if we want to work out what log base 2 of 15 is, we can't do that directly on most calculators. So to change the base from some base b, like 2 in this example, to some other base a, like 10 or e that we can use on our calculator, we start off by writing the log that we're trying to figure out as m, where m is the number we're trying to find. We can then rewrite that equation as b to the power of m is equal to x. We can then take log base a of both sides of that equation, and then we can use our log law to bring the m out of the log on the right hand side. Making m the subject there, we'll get m is equal to the ratio of those two logs. And then the m is, of course, what we're trying to find. That is log base b of x. So there we've changed the base from log base b, like 2 in the example, to some other base, like 10 or e, that we can calculate on our calculator. So we'll evaluate log base 2 of 15 in this example. So to solve that, we set log base 2 of 15 to equal m. M is what we're trying to find. And we'll rewrite that as an indicial equation. 2 to the power of m is equal to 15. We can then take log base 10 of both sides so that we get this expression. Now we can use our log laws here and take the m out and multiply it by the log of 2. And then we can make m the subject to get that expression. And of course the m is what we were trying to find. M is log base 2 of 15. So that gives us an expression now for log base 2 of 15 in terms of a base that we can find on most calculators, in this case base 10. We can evaluate that out now on a calculator to get an answer of 3.907. We could use base e in that last example instead of base 10, and so we would get this expression here, where we're now using log base e. And once again, when we evaluate that on a calculator, we get the same result of 3.907. So we've seen in this lesson how we can change the base of a logarithm from some base b to some other base a, which is very useful for evaluating the logs when we don't have base b on our calculator. So we might change those to base 10 or base e. We've solved exponential equations by taking logs firstly, and we've solved log equations using the log laws.